Okay, so welcome to our Chapter 5, 6, and 7 exam review. What I'm going to be talking about, I'm going to talk a little bit about the exam, let you know just kind of an overview, go through some of the content that I expect you to be able to do, and then we'll go through and look at the sample questions for the exam, okay? So we'll start out with just Chapter 5, and it's right here. I want you to determine if an operation forms an inner product. So that we've seen some different operations that could form inner products. We've got those 4 requirements for being an inner product. So make sure that you know what those 4 are and that you can actually just show that something actually does fulfill that requirement for the inner product. Find the inner product given an operation. So I give you a product, an operation that is an inner product, and I give you, say, for example, like a set of functions, and I say, go find the inner product, you can go out and do that. So, basically that you can use an inner product when you're given it. Find the dot product and magnitude using the dot product. Okay. So basically, can you take the dot product? Can you find the magnitude? Should be pretty straightforward. Determine whether or not vectors are orthogonal. Same thing, right? Take the dot product, see if it equals 0. If it equals 0, they're orthogonal. Form an orthonormal basis from a basis using the Schmidt process. Or you can also find maybe an orthogonal basis as well. It doesn't necessarily have to be orthonormal, but you should know what I mean by both of those things, and you should be able to use the Schmidt process. Okay? Expect that the Schmidt process will probably be for, I don't know, in R3. Most likely something along those lines. Not for a strange inner product, just the dot product we're going to use the Schmidt process for. Okay? Find the distance from a point to a plane or a point to a line. And so that is an application of projections and orthogonal projections, and that's what I expect you to be able to do as well. So, Chapter 6, I want you to verify a transformation is a linear transformation. And so basically that is proving that the transformation is closed under addition and it's closed under scalar multiplication. And those are the 2 requirements for something to be a linear transformation. Determine the matrix of a transformation from the transformation. Okay, and so what I'm talking about that is, I give you a linear transformation. You can form a matrix of the transformation from the linear transformation in Rn, in Cn, so complex over the complex numbers, or inside of PNR, so the set of polynomials. And yeah, there we are. And then determine the linear transformation from the matrix of the transformation. So you've got it, give it a matrix. Can you actually form the transformation? And you should be able to do that for those 3 vector spaces, 3 sets of vector spaces as well. Rn, Cn, and PNR. Okay? Determine the value of a vector under the linear transformation. And so again, that's all vector spaces. So you're given a linear transformation. Tell me what the value of the vector is. Okay, under that linear transformation. Find the kernel in the range of the transformation T. Determine if a transformation T is 1-to-1 onto or a linear transformation. And determine if a transformation has an inverse and find the inverse of the transformation. Okay? I should add in there, you should be able to, and you'll see we'll have a practice problem like this, is that if you are given a, if you find the inverse transformation, can you actually take a vector backwards, right? Using the inverse. And then Chapter 7, you want to find the eigenvalues and eigenvectors of a matrix A. You want to consider the algebraic multiplicity, the geometric multiplicity, the eigenspaces, an eigenbasis if applicable. Determine if a matrix is defective or non-defective. And then find the diagonalization of a non-defective matrix. Okay, so those are what we want from Chapter 7. So it's pretty much everything that I went over inside of those 3 videos. For the eigenvalues and eigenvectors, you may be asked to find them by hand. Okay? So on the one hand, for a significant amount of the exam, you'll be able to use calculators or a computer in order to do the work of the exam. But then when it comes to finding eigenvalues and eigenvectors, you're going to have to do that by hand. Same thing with like being able to find the dot product or the magnitude of a vector. That sort of thing. Okay? All right. But row reduction definitely can be done utilizing a computer. And in addition to that, if you want to use, if you're allowed to use it right? You can use a computer in order to find eigenvectors and eigenvalues, as long as I don't ask you to do it by hand. But you should be able to find eigenvalues and eigenvectors by hand, okay? So that is definitely something you should be able to do. All right, so that's just kind of like the overview. It's sitting right there. It's all there. So, you know, I just wanted to make sure that if you had any questions, if you wanted some clarification on what that meant, that's what I mean by those things, okay? All right, so let's find an orthogonal basis for the span of the set S in the vector space V. And so let's consider that we have this set 6, -3, 2, 1, 1, 1, 1, -8, -1. What you should definitely be thinking to yourself is, I need to go through and use the Gram-Schmidt process. If you're looking for an orthogonal basis from a non-orthogonal basis, you're using the Gram-Schmidt process. So in order to do that, we're going to start out with our first vector in the set is going to just be 6, -3, 2. And then we'll orthogonalize all the other vectors in the set off of V1. So what I want to do now is V2 is then going to equal, so it'll equal V1, or excuse me, X1, so that's 1, 1, 1, okay, minus, and then we'll take the dot product of 6, -3, 2, that's actually V1, dotted with 1, 1, 1, divided by the magnitude of 6, -3, 2 squared. And then we'll multiply that then by V1. So that's 6, -3, 2. When we do that, we're going to get then 1, 1, 1 minus, and then this is going to be 6 - 3 plus 2 divided by, and if we just square it, we're going to get 6 squared plus -3 squared plus 2 squared times 6, -3, 2. Okay? This is then going to equal 1, 1, 1 minus, and that'll be 5 over 49 times 6, -3, 2, which ends up equaling, this equals 19 out of 49, 64 out of 49, and 39 out of 49. So now what we'll do is that we'll take that and we'll add that to our set of vectors. It's now one of our orthogonal set. And now we've just got to go find V3 because we're looking for a basis in R3, so we need three three-dimensional vectors in R3. So we'll take V3, and V3 is going to end up being, so we're going to start out with X3, 1, -8, -1, and we'll subtract from that. We're going to take the dot product, where we're going to take the orthogonal projection of X3 onto V1. So that's going to be 6, -3, 2. That's V1. And we're going to dot that with 1, -8, -1. And then we're going to divide that through by the magnitude of 6, -3, 2 squared. And then multiply that by 6, -3, 2. And then we're going to subtract from that, we're going to subtract the orthogonal projection of X3 onto V2. So now we're going to have, that's going to give me the dot product of, and we're going to utilize V2. So this is going to be 19, 49, 49ths, 64, 49ths, 39, 49ths, dotted with 1, -8, -1, divided by the magnitude of, and this will be the magnitude of V2, so this is going to be 19 over 49, 64 over 49, 39 over 40. And then we'll multiply that by the vector 19 over 49, 64 over 49, 39 over 49. Okay, so it's a little involved, so what I'm going to do is just, you know, I'm going to kind of pause for just a second and go through and do some of my calculations. Just remember, how do we find the dot product? All right, so that's the Gram-Schmidt process. You need to know how to do that. So when we go in and we actually calculate, do some of the calculation here, what we're going to get is we're going to get our 8, negative 1. That's our first vector, minus 4 sevenths, 6, negative 3, 2. Plus, and then we'll be 266 over 61 times 19 over 49, 64 over 49, 39 over 49. Okay? And then we're going to get this 1, negative 8, negative 1, minus 24, 7, negative 12, 7, 8, 7, plus 722 over 427, 242 over 427, and 1482 over 427. So that's going to end up giving us 1 over 427, and this is negative 315, negative 252, 567. So that's going to be my third vector. So what I'm going to do, I'm going to put them all together. And what I'm actually going to do, I'm going to pull off the scalar, because I don't actually need the scalar for the basis vector. I just need this direction. And then I'm also going to pull off the 49 scalar out of the second basis vector. So when I put them all together, my basis will be 6, negative 3, 2, 19, 64, 39, negative 315, negative 252, 567. Okay? And that is the orthogonal basis for our vector space V. Okay? And there you go. All right, let's suppose we want to find the distance from the point 2, 3, 4 to the line in R3 passing through 0, 0, 0, and 6, negative 1, negative 4. So what I'm going to do is I'm just going to imagine I've got 0, 0, 0, and you don't have to actually draw the graph, but I'm just doing that for our purposes. And I'm going to imagine that I'm going to create a vector, and here's my point, by the way, 2, 3, 4. And then I'll have over here, this is 6, negative 1, negative 4. Okay? Just to be consistent with our book, this was P, this is Q, okay? And we're going to create a vector W here with PQ and this point here, which we'll call it R. There you go, okay? So we're going to create that vector W, and the idea here is we're going to project down onto the line. We're going to project W down onto the line, onto the vector PQ, and then we're going to take W minus that projection. Okay, so that's going to be our deal here. This thing here is going to be the projection of W onto PQ. Okay, and then we're going to be looking for the magnitude of W minus minus the projection of W onto PQ, and that's going to be our goal. So what we need to do first is we actually need to find these two vectors. So I'm going to find PQ first. So PQ is going to equal, right, 6 minus 0, negative 1 minus 0, and negative 4 minus 0. Okay, so it's going to end up being 6, negative 1, negative 4. And then W is going to end up equaling 2 minus 0, 3 minus 0, 4 minus 0. Okay, so you're just going to pick, a point on PQ. Okay, and you're going to draw the vector from the point that we're looking to find the distance from to that point. It's going to give you your other vector. And this is going to be 2, 3, 4. So now we need to find the projection. All right, so the projection of W onto PQ is going to equal, it's going to be the dot product of PQ with W, okay, divided by the magnitude of PQ squared times PQ. Okay, so first we'll find that dot product. So PQ dotted with W is going to end up equaling, we've got 6, negative 1, negative 4, 2, 3, 4. So this is going to be 12 minus 3 plus 16. So we're going to get 12 minus 3 minus 16, and that's going to end up equaling, that's positive 9 minus 16, so it's going to end up being negative 7. And then we're now going to find the magnitude of PQ squared, which ends up equaling 6 squared plus negative 1 squared plus negative 4 squared. So that's 36 plus 1 plus 16, which equals 53. So this term here is going to be negative 7 over 53. So we get negative 7 over 53, and then we'll multiply that by PQ. And remember, PQ is 6, negative 1, negative 4. And so that's negative 42 over 53, 7 over 53, 28 over 53. We'll just go through, check that. 42 over 53, 7 over 53, plus 28 over 53. Great. And now we just need to go out, we need to find the subtraction of W minus P, the projection. So W minus the projection, so this is going to be 2, 3, 4, minus negative 42 over 53, 7 over 53, 28 over 53. We'll find the magnitude of that in just a moment. But first we're going to do the subtraction. So that gives me, this ends up giving me 148 over 53, comma, 152 over 53, and 184 over 53. Just go and find the magnitude of that. Right, so that's going to end up being the square root of 148 over 53 squared plus 152 over 53 squared plus 184 over 53 squared. Or you can just put it obviously over 53. And we go through and we do that math. That ends up equaling 5.2986 if we go down to 4 decimal places, and there we go. Okay, so what you'll do is you'll actually, I mean, depending upon whether or not you're actually given a vector or you need to find a vector, or need to find some vectors, you're essentially going to draw a vector from the point down to the line, okay? Then you're going to find a projection of that resulting vector onto the original vector or original line of vectors, okay, using that projection formula. Then it is essentially it's going to be the vector W minus the projection, and then we just go out and find a magnitude, and that actually gives me the value of the distance from the point to the plane. So what we're going to do now is we're going to find an equation from the point 0, 0, 0 to the plane with the equation 2x minus y plus 3z equals 6. So we're going to just draw a little plane just to kind of demonstrate what it is that we're going to do now. Okay. So here, by the way, this is the normal vector. And we know that the normal vector, if we know the equation for our plane, our normal vector is going to be 2, negative 1, 3. Okay, so there's 2, negative 1, 3. That's the value for the normal vector. And what we're going to need to do is we're going to imagine here's 0, 0, 0, for example. And I'm going to pick a point that's actually on the plane. And so for me, the easiest thing to do in terms of a point on the plane, let's just say that y and z are equal to 0. So I've got 2x minus 0 plus 3 times 0 equals 6. So that means 2x equals 6. So x equals 3. Okay, so that means we've got on the point, we've got the point 3, 0, 0. All right, so we got point 3, 0, 0. I'm going to imagine that's on the plane. I'm going to draw a vector from 0, 0, 0 to 3, 0, 0. Yay, there we are. Okay, so that vector, by the way, we'll call that W. Okay, so W is just going to equal, right, it's just 3, 0, 0. Here's my normal, call that N, and that's 2, negative 1, 3. What I'm going to do is I'm going to project 3, 0, 0 onto N. Okay, so I'm going to take the projection of W onto N. Okay, and that's actually going to give me my distance. So what we'll do is we're going to take the dot product, 3, 0, 0, and 2, negative 1, 3. Since we're projecting onto N, what we need to do is we're going to divide through by the magnitude of N. So that's the magnitude of N, or N squared. Okay, and then we'll multiply that by N. So that's 2, negative 1, 3, because that's the direction. And then, actually, because we're going to be looking for the magnitude of it, right, because we want to know that distance, we'll take the magnitude. So we get, now, first take that dot product, so that's going to be 6, and then plus 0, okay? So 6 divided by, and this is going to be, since this is squared, in fact, this is going to be 2 squared plus negative 1 squared plus 3 squared. Okay, times 2, negative 1, 3. So this is 6, and this is 4, 5, and 14. So 6 over 14 times 2, negative 1, 3. And what I'll do, right, is, so I'll multiply that all in because I'm going to have to find its magnitude. So that's going to give me 6/7, negative 3/7, 9/7. And so its magnitude then is going to end up being the square root of, well, it'll all end up being over 7 eventually because these are all over 7. We're going to square it and then take the square root. So it's going to be 6 squared plus negative 3 squared plus 9 squared. And so that ends up giving me the square root of 126 over 7, which equals 1.603567. Or, well, let's just go out to 4 decimal places, 1.6036. Okay? So what we're going to do here is essentially, if you want to get a kind of a formula here for this, we're going to have it be, it's going to be the magnitude of P W onto the normal N. Okay? And that is the distance from the plane to the point. Or from the point to the plane, excuse me. All right, let's suppose that a matrix A has the eigenvalues negative 3 and 1 with an algebraic multiplicity of 2. So that's saying that 1 has an algebraic multiplicity of 2, if you remember that n equals 2. And we have associated eigenvectors 1, 0, 2, 2, negative 1, 2, and 0, negative 1, 0, respectively. Let's write the diagonalization of A, and then we're going to go find A. Okay? So what we're going to need to do is I'm going to first, I'm going to generate A, or excuse me, I'm going to remember that A is going to equal SDS inverse or PDP inverse, depending upon how you want to look at things. And so S is going to be the matrix of the eigenvectors, and that's going to be 1, 0, 2, 2, negative 1, 2, 0, negative 1, 0. And then what I'm going to do is I'm going to set up what D is. D is my diagonal matrix, so D is going to equal, and I just have to remember that I have to have it in the proper order. So negative 3 is my first vector, and then 1 has an algebraic multiplicity of 2, so that means that we're going to have 2 values along the diagonal. So this is 0, 0, 0, 0, 0, 0. There we are. So there's D. And then we have S inverse, and S inverse is going to be the inverse of 1, 2, 0, 0, negative 1, negative 1, 2, 2, 0. So we're going to use a calculator to find that. And so after doing that, what I get is I get negative 1, 0, 1, 1, 0, negative 1 half, negative 1, negative 1, 1 half. Now A is going to equal SDS inverse, so that's the diagonalization of A. So we have A equals, and I've got 1, 2, 0, 0, negative 1, negative 1, 2, 2, 0. Negative 3, 0, 0, 0, 1, 0, 0, 0, 1. Negative 1, 0, 1, 1, 0, negative 1 half. Negative 1, negative 1, 1 half. And then to find what A is, I just have to multiply those three together. Plug that into our calculator and we get 5, 0, negative 4, 0, 1, 0, 8, 0, negative 7. So let's suppose now we're looking at number 5, that t goes from P2R to P2R, and it's defined as P of ax squared plus bx plus c, and that equals 2a minus bx squared plus 3a plus 3cx plus a minus 2b minus 3c. We want to find the kernel of t and the range of t. We want to ask ourselves, is t an isomorphism, and then how do you know? If t is an isomorphism, find the inverse of t. So what I'm going to do here first is I'm actually going to proceed by finding the matrix of the transformation. Okay. So what I'm going to do, I'm going to find A. Now A, I'm actually going to read this off, and I'm going to have in A first that A is going to be 3 by 3 because I'm going to go from P2R to P2R. That's a 3 by 3. These are three-dimensional space, and this is three-dimensional as well. So we're going to have A be 3 by 3. The bottom row is going to be my x squared rows. The middle row, x rows. Top row is the 1 rows. Okay. And then in terms of, if I kind of want to think about it in terms of my columns, I've got A, B, and C here. Okay. So I'll start over here. All right. And that's 1, negative 2, negative 3. That's going to be the first row. Then I'm going to have 3, 0, 3. And then I'm going to have 2, negative 1, 0. And that's going to be A. Okay? And A is going to be what I actually kind of like base everything off of. I'm going to determine the kernel of T, the range of T, all utilizing A, because it turns out that this matrix is the matrix of the transformation. So 1x and x squared. Okay? So remember that the kernel of T, we need to see that the kernel of T equals 0. Okay? That's going to end up telling me that T is 1 to 1. So I want to take a look at that. And then also if the range of T, in this case, equals P2R, right, because that's our codomain, then T is on 2. And if T is 1 to 1 and on 2, then T is an isomorphism. Okay, so just as a reminder, that's what we need. So I'm going to go in here, and in order to find the kernel of T, I'm going to find the null space of A. So I'm going to find the RREF of A. Okay, I'm going to need to use that too because the range of T is going to be the call space of A as well. Okay, so the range of T, our REF of A. So now when I take the RREF of A, what I get is I get 1, 0, 1, 0, 1, 2, 0, 0, 0. Okay, and so my null space of A, which is going to be my kernel of T, all right, we'll just turn that into the kernel of T in just a moment, is going to end up being, we're going to have x1 plus x3 equals 0, and we'll have x1 plus 2x3 equals 0. So x3 is going to be free, so we get x1 equals, we'll actually let first x3 equal s, so x1 is going to equal negative s, x2 is going to equal negative 2s. So my null space is going to be, the basis for my null space is going to end up being negative 1, negative 2, 1. And that's the basis for my null space. Okay? So now notice that the kernel of T is not equal to the 0 vector, right? So what we have here is T is not 1 to 1 because the kernel of T does not equal the 0 vector. Okay, so not 1 to 1. Now I'm going to go back to my RREF of A in order to help me find the range of T. The range of T is going to be the call space of A. So before I do that, I should change this back into a vector in P2R. So essentially what we have here is that the kernel of T, okay, is going to equal, and so remember this is going to be your constant. The first term is the constant, then the x term, then the x squared. So the kernel of T is going to be negative, we'll actually start out with the x squareds, is going to be x squared minus 2x minus 1. And so that ends up being the basis for the kernel of T. Right? So you can put the span on it, you don't have to put the span on it. We kind of get the idea that that's going to be the basis for the kernel of T. Now the range of T, okay, is going to be the call space of A. And so we look at the call space of A. I've got a pivot here in the first column. I've got a pivot in the second column. So the range of T, if we write it, the call space of A is going to equal, as a basis, is going to be 1, 3, 2, and negative 2, 0, 1. Negative 1, excuse me. Negative 2, 0, negative 1. So the range of T, if I rewrite these as polynomials, this is going to be 2x squared plus 3x plus 1, and then negative x minus, or negative x squared, right, minus 2. And that's the basis for the range of T. And notice that there's only 2 vectors there in from P2R. Okay, there's only 2 vectors from P2R. So what we notice here is the range of T does not equal P2R, as there are only 2 vectors in the range of T. You need 3 of them for P2R. So T is not on 2. Since T is not on 2 and T is not 1 to 1, T is not an isomorphism because T is not onto or 1 to 1. So T does not have an inverse. And there we go. All right. So a couple things to remember here about this one, right? We want to make sure that we can actually transform a polynomial linear transformation into a matrix, because that's going to be probably the easiest way. In fact, in my opinion, it's the easiest way to go out and find the kernel of T and the call space of A, or excuse me, the kernel of T and the range of T. We have these things, these requirements. The kernel of T equals 0 for T to be 1 to 1. The range of T has to equal P2R or equal W, right? The codomain in order for T to be onto. And T has to be 1 to 1 and onto for T to be an isomorphism. So my null space, right? The null space of A, once we find that, we can translate it back into the kernel of T. We can translate it back into polynomials, and that's the kernel of T. And we can do the same thing once we find the call space of A. That ends up being the range of T, and we can transform those back into polynomials as well. Just a quick thing to remember, when you're looking at a set of polynomials, right, or you're looking at a vector, this is your x squared term, or you start up at the constant. The constant term is always the first term. Then we have the x term, then x squared, and if we happen to have a larger space, then we can go out x cubed, x to the fourth, etc., whatever. Okay? All right. All right, so now let's look at number 6. And so what we've got here is we've got some questions about eigenvalues and eigenvectors. We've got a matrix A, and we've got some just general questions. To find the eigenvalues of A, we set, and this is going to be the determinant of A minus lambda I equal to 0, and solve for lambda. Okay, so that's our first step inside of solving for our eigenvalues. Okay, and then we use the determinant of A minus lambda I to give me, or excuse me, the null space of A minus lambda I to give me the eigenvectors, etc., etc. Okay, let's suppose that the characteristic polynomial for A is -1 minus lambda, -2 minus lambda, 3 minus lambda. Okay. So what we've got here now is we're given the characteristic polynomial. So that means that if I look at B here, I'm going to have that lambda 1 is going to equal -1. Lambda 2 is going to equal -2. And lambda 3 is going to equal 3. So those are my 3 eigenvectors. And cool thing about that is because I know that I've got 3 eigenvectors, I'm going to get, or excuse me, eigenvalues, I'm going to get 3 eigenvectors. Consequently, and this is in R3, so what I'm going to get is I'm going to get a non-defective matrix. I'm going to be able to diagonalize. All right, and I should know that already because I've got 3 distinct eigenvectors, eigenvalues. Okay, so we now want to find the eigenvalues and eigenvectors for A. Show all your work. How did we do that? Right, okay, just as a review, -1 minus lambda, set that equal to 0. Right, and we're going to get -2 minus lambda, set it equal to 0, and 3 minus lambda equal to 0. And that's because the characteristic equation should be set equal to 0 to find lambda. Okay? Now, what I want to do is I'm going to plug into A minus lambda, okay, each of my lambdas. So I'll start out with lambda 1 equals -1. And so I'm going to subtract -1 from the diagonal. So I got -1 minus a -1, 1, 0, 1, 2 minus a -1, 1, 0, 3, -1 minus a -1. This ends up equaling 0, 1, 0, 1, 3, 1, 0, 3, and then also 0. Okay? Now, what I need to do now is I need to find the null space of this. Right? This is A plus 1i. Okay, that's actually, or the, yeah, that's A plus 1i. So I want to find the RREF of A plus 1i. Okay, in order to find my null space. So I'm going to go in and do that. And when I do that, what I get is I get 1, 0, 1, 0, 1, 0, 0, 0, 0. So that tells me actually that x3 is going to be free. I get x1, plus x3 equals 0, and I get x2 equals 0. So if I let x3 equal s, x1 will equal negative s, x2 equals 0, x3 equals s. So the basis for my null space, and consequently my eigenvector v1, is going to equal the vector negative 1, 0, 1. Okay? Now I'm going to take lambda equals, I'm going to go to lambda equals negative 2. I'm going to do the same process. So I got lambda equals negative 2. I'm going to subtract from the diagonal, okay, negative 2. So what that's going to give me then is, that's going to give me I got negative 1 minus a negative 2, so it's positive 1, 1, 0, 1, 4, 1, and 0, 3, 1. I'll go in, row reduce that. And when I do that, what I get is, okay, so the RREF here in this case of, and this is a plus 2i, ends up equaling then 1, 0, negative 1/3, 0, 1, 1/3, 0, 0, 0. So if I rewrite as my null space, I get x1 minus 1/3 x3 equals 0. x2 plus 1/3 x3 equals 0. And we'll let x3 equal s. So we've got, I'll just, x1 equals 1/3 s, x2 equals negative 1/3 s, and x3 equals s. Okay, so what I get is I get the vector then v2, my second eigenvector, is going to be 1/3, negative 1/3, 1. And I'm actually just going to rewrite that as, I'm going to let v2 then equal 1, negative 1, 3. Right, just by multiplying by 3, I get the same eigenvector, going to have the same characteristics and qualities, just gives me whole number values now. Okay, so there's v2. Now let's go find v3. We'll go back up. Want to see that L3 is equal to 3. So L3 equals 3. I'm going to now subtract 3 from my diagonal. So I got negative 1 minus 3 is going to end up equaling negative 4. Okay, just negative 1 minus 3 equals 4, and then 1, 0. Second line, 1, 2 minus 3 is going to be negative 1, 1. So 1, negative 1, 1. Confirm that's the case. 1, negative 1, 1. And then 0, 1, negative 4. Or excuse me, 0, 3, negative 4. We'll take this now, the RREF of A minus 3i, which is what this matrix is. It ends up giving me 1, 0, negative 1/3, 0, 1, negative 4/3, 0, 0, 0. So rewriting, finding my null space, x1 minus 1/3, x3 equals 0, x2 minus 4/3, x3 equals 0, and x3 equals s. So x1 is going to equal 1/3 x3, x2 is going to equal 4/3 x3, okay, or rather s, right, because we changed x3 to s, and then x3 is s. So the vector v3 now is going to equal 1/3, 4/3, 1. And I'm actually just going to change that. I'm going to let v3 then equal 1, 4, and 3. Excuse me, 1, 4, and 3. Okay, so those are v1, v2, and v3. Okay, I've got v1, v2, v3. The method here is to subtract my eigenvalue from the diagonal, find the reduced row echelon form of that matrix, right? And then find the null space using that reduced row echelon form, right? The null space will then be your eigenvector, right? Or eigenvectors if there's more than one of them. I'll accept either one of these, either 1/3, -1/3 1, or 1, -1 3. Doesn't matter to me. Sometimes just like it cleaner. So there it is. Oftentimes you also see this in like solution books, things like that. All right. So we've done that now. Okay. Let's kind of write these down. I'm going to start out with -1, 0, 1. That's lambda equals -1. So here are eigenvectors and eigenvalues. Now what we want to do, it says here for C, is prove that the vectors you found in B are the eigenvectors using the definition of an eigenvector. So we're going to go back to A. I'm going to actually pull down A. So we have that for each one of them. And so what we need to do is we need to show that A times V1 equals -1 times V1. Okay? So we'll take this, we'll take A. That's -1, 1, 0. 1, 2, 1, 0, 3, -1 times -1, 0, 1. And what we get here is we get 1 plus 0 plus 0, so that's 1. Then 1 times -1 plus 2 times 0 plus 1, that ends up being 0. And then 0 times -1 is 0, plus 3 times 0 is 0, and -1 times 1 is -1. Now notice that this is in fact -1 times -1, 0, 1. Okay, so V1 is an eigenvector. And lambda equals -1 is its eigenvalue. Done. Good. Let's go down to L2. L2, we take this, we've got -1, 1, 0, 1, 2, 1, 0, 3, -1. Multiply it now by, in this case, 1, -1, 3. And this will then equal, we get -1 plus -1 is -2, so this is -2. 1 times 1 is 1. 2 times, so I'm going to write this down, 1 minus 2 plus 3. Okay, so that's -1 plus 3, that's +2. That equals +2. Okay, and then 0 plus -3 is -3 plus -3 is -6. So we got -2 to -6, and if we notice that that is in fact -2 times 1, -1, 3. Great. So V2 now we see as an eigenvector, and lambda equal to, right, V2 is an eigenvector, and lambda equal to -2 is its associated eigenvalue. Okay. Now finally, last, we're going to take -1, 1, 0, 1, 2, 1, A, in other words, 3, -1. We'll multiply that now by 1, 4, 3. 1, 4, 3. This is going to now equal, we'll take, it's going to -1 plus 4 is going to end up being 3. And then 1 times 1 is 1, 2 times 4 is 8. So 1 plus 8 is, let me just write this all down, 1 plus 8 plus 3 equals 12. And then 0 plus 12 plus -3 is going to equal 9. And this is 3 times 3, or 1, 4, 3. You see that 3, 12, and 9 is 3 times 1, 4, 3. So V3 is an eigenvector. Cool. So what we've done is we've actually proven that these 3 eigenvectors are in fact eigenvectors, and we've proven their associated eigenvalues. We're now asked, is A defective or non-defective, and explain how you know. There's a lot of different ways that we can actually say this is the case. So let's just kind of review what each one is. One, I can state that as A, or as A is 3 by 3, okay, and we have 3 distinct eigenvalues, then, okay, we have 3 eigenvectors. and A is non-defective. Okay? Basically, what we see here is like the n here, okay, is equal to the number of eigenvectors that we have. All right? And so consequently, A is non-defective. We can also write, for example, that Ni equals Mi, right? Because Ni equals 1, Mi equals 1. Our algebraic and geometric multiplicities are the same. So for all our eigenvalues, so A is non-defective. That's another one, right? We have basically the algebraic and geometric multiplicities have to equal each other in order for our matrix to be non-defective. Or, okay, we can construct an eigenbasis, okay? We can construct an eigenbasis, right? And that eigenbasis is going to end up being our eigenvector. So it's going to be -1, 0, 1, comma 1, -1, 3, 1, 4, 3 from the eigenvectors of A. So A is non-defective. Yay. Okay? So, yes, A is non-defective. Essentially how you know that is because since A is 3 by 3, if we have 3 eigenvectors, then in fact A is going to be non-defective. Okay, so now if A is diagonalizable, find the matrices S and D such that you can diagonalize A. So S is going to be the matrix of our eigenvectors. This is going to be -1, 0, 1, 1, -1, 3, 1, 4, 3, your matrix of your eigenvectors. And then D is going to be the matrix of your eigenvalues. Just make sure that they're in the right order. Okay, they're in the right order. So remember, this is lambda equals -1. This is lambda equals -2. And this is lambda equals -3. So this is going to be -1, 0, 0, 0, -2, that's not -3, this is 0, lambda equals 3, 0, and 0, 0, 3. And those are your eigenvalues. They constitute the diagonal of D. And those are your matrices S and D. Okay? So this actually, we went over a bunch of things, especially doing a lot of stuff by hand when it comes to eigenvectors and eigenvalues. So a little bit longer in terms of the explanation. All right, let's look at number 7. Let's suppose that we have the matrix of the transformation A equal to -1, 2, 0, 2, -1, 2, 4, 1, 9, 1, 0, 2. So the first thing that I want to do is I want to go in and I want to find the RREF of A, because the kernel of T is just simply going to be the null space of A. So the RREF of A is 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 0, 0, 0. Okay? So the null space of A is equal to the 0 vector. And that means that the kernel of T is also equal to the 0 vector. So there we are. And then if we look at the range of T, the range of T is going to be basically the call space of A in this case, because we're really just looking at the matrix. So the call space of A, which in this case is going to actually equal the range of T, is equal to the vectors -1, 2, 4, 1, to -1, 1, 0, and 0, 2, 9, 2. And so if you remember, right, to find the call space, we take all of the columns that have pivots and we refer back to A, and that ends up giving me the call space of A. Now, to prove that A is 1 to 1, we need that the kernel of T has to equal the 0 vector. Okay, so since kernel of T is equal to the 0 vector, okay, then A is 1 to 1. There it is. That's it. And then if we want to prove that, or disprove that A is onto, we need to know that the range of the range of T is equal to, in this case, it would be R4, because we want to know the space is, because A is going to take us from R3 into R4. So T, right, goes from R3 into R4. And before I go anywhere, let's actually just explain that. The reason why is because your input vectors are going to be in R3, x1, x2, x3. And your output vectors, right, are going to be in R4, v1, v2, v3, v4. So your domain is going to end up being R3, and your codomain is going to end up being R4. Okay, so domain's R3, codomain's R4. And so, if we look here, what I've got is I've got 3 vectors. In that basis, I've got 3 vectors that are in R4. So that's actually not all of R4. So, the range of T does not equal R4. Thus, T is not on 2. So in order for T to be on 2, we need that the range of the transformation is all of the codomain. Okay? And in this case, it is not. Right? Range of T is a 3-dimensional subspace of R4. Okay? All right. And is T an isomorphism? Is A an isomorphism? The answer is no, as A is not on 2. To be an isomorphism, A actually needs to be both 1-to-1 and on 2. It needs to be a bijection, and in this case, it's not a bijection. So consequently, we have a so our transformation is not an isomorphism. So as A is not on 2, A is not an isomorphism. And there we go. All right, so now number 8. What we have here is we want to suppose that T from P1R to R2 is defined as the linear transformation T of AX plus B equal to B minus A 2A. And so we first want to find the matrix representation of T, and we're going to show all of our work. Okay. There are a couple different ways. I'm going to give you the one in which we use the standard basis for P1R. So we're going to first find Tx. So Tx is basically just T of 1x plus 0. So basically that's A equals 1 and B equals 0. Okay, so that's Tx, and that's going to be, by the way, that actually is going to go along with 0, 1. If you remember, constant and then the x term. So A equals 1, B equals 0, and that's going to end up equaling, so we'll get B minus A, so that's going to be 0 minus 1, and then 2A is going to be 2 times 1. So what we're left with is negative 1, 2. If we take T1, which actually is going to be our first vector, T1 is, and I'm going to write this as a column vector. So this is going to be negative 1, 2. And so actually our first vector, T1, is just going to equal T times 0x plus 1. So that means A equals 0 and B equals 1. So we're just using this definition. And that'll equal then 1 minus 0 and 2 times 0, which equals 1, 0. Now, will the 1's come first, the x's come second, and when we're talking about the standard basis for polynomials. So my matrix of the transformation, A, is equal to 1, 0, negative 1, 2. And there we are. Okay, so basically all we've got to do is know what our standard basis is, right? Be able to translate our linear transformation, okay? And then generate our vectors in the new space using the transformation. And there's our vectors. Now, using T, determine the following and justify your reasoning in complete sentences. So what I'm going to do is I need to figure out, okay, using my transformation T, or my matrix representation A, right, we're going to first find the RAF of A because we're going to need that in order to find the kernel of T and the and the range of t. So the RIF of A is 1, 0, 0, 1, okay? And so that actually means that the kernel of t equals the 0 vector. Okay, because the null space is equal to the 0 vector. It's got only the trivial solution to the homogeneous differential homogeneous equation. So kernel of t equals 0, so t is 1 to 1. Okay? Yeah. If you get the identity matrix, you've got null space equal to 0. Is t onto? Well, yeah. Range of t, in this case, equals the call space of A, which is just equal to R2. How do we know? I've got 1, 2 vectors in R2. So consequently, the basis is going to end up being all of R2, right? If we went back, we'd see that these two vectors, they're going to be the call space of A. There's 2 of them in R2, so it's all of R2. Okay? So range of t equals R2, so t is onto. Is t an isomorphism? Yes. Okay? As t is 1 to 1 and onto, t is an isomorphism. Okay? And if t is an isomorphism, we need to find t inverse. So what we'll do is we'll go find A inverse. Okay? So first things first, understand that t is now going to go, t inverse is going to go from R2 to P1R. So t inverse goes from R2 into P1R. Okay? I'll first find the inverse inverse matrix. So, and that inverse, so A inverse is going to equal 1, 0, negative 1, 2. Or excuse me, that's the original matrix, is going to end up being 1, 1 half, 0, 1 half. So we're now going to find our linear transformation. We're going to get 1, 1 half, 0, 1 half. And we're going to multiply, we're just going to multiply by A and B. Like we did before, we'll make that our input. And this is then going to give me A plus 1 half B and 0 plus 1 half B, so that's 1 half B. So consequently, what I get here is if you look at this and you say, okay, well, what is that as a polynomial? So we're going to take t of AB, that's our input, is going to end up equaling, here's the constant term, because that's the top, and the bottom term is going to end up being my x term. So that's going to end up equaling A plus 1 half B plus 1 half BX. And that is our inverse of the transformation. So we go in, we find the inverse of A, right? We found A, we find the inverse of A. Once we found the inverse of A, you just plug in, choose like a, since we're going to R2, you'll pick a vector in R2. Could call it x1, x2. I'm calling it an AB because that's what we used before. And then we'll get an output vector, and then that output vector is going to end up being the output for our linear transformation. Just remember that we've got to translate it in terms of a polynomial. Question number 10. We've got tv to w, and it's going to give me t of c plus bx plus ax squared, and that equals b minus 2a, 2c, and 2a minus 3b plus c. So what we're asked first is what is v and what is w? So what is our domain, v, and what is our codomain, w? Notice that our domain is going to end up being a polynomial, a second degree polynomial. And so v is going to equal p2r. And w, notice, is a vector in R3, so that's going to be R3. And there it is. Okay? Now, we're being asked to find A, the matrix of the linear transformation. So what we're going to do then is we can use this, we can use the standard basis vectors for a polynomial. So we'll start out with t of 1. And t of 1, just to help us define this, is going to be that where c is equal to 1, b is equal to 0, and a is equal to 0. Okay? So we're going to use that definition of the polynomial. So t of 1 is going to end up equaling 0, 2, 1. Right? Just plug in c equals 1 into the vector, you get 0, 2, 1. T of x then is going to end up being, we're going to have c equals 0, b equals 1, and a equals 0. So t of x is going to end up equaling 1, 0, 2. Or excuse me, 1, 0, negative 3. And now we need to find t of x squared. T of x squared then is going to have that c equals 0, b equals 0, and a equals 1. So if we look then, we've now got a equals 1, so that's going to give me negative 2, 0, 2. So I got negative 2, 0, 2. So those are the transformation, the standard basis vectors for P2R under the transformation. All I've got to do in order to find a is I've just got to put those in order. So a is going to equal, the 1 for 1 comes first, 0, 2, 1. Then x, 1, 0, negative 3. And then x squared is negative 2, 0, 2. And there's a. Okay? So use the standard basis vectors and the transformation in order to find the transformation, the standard basis vectors under the transformation, and then you just put them together, and that gives you a. Okay? Now the kernel of t. So in order to find the kernel of t, we're going to have to find the null space of a. And so we're going to have to take we're going to have to do reduced row echelon form for this matrix. When I do, my RREF of a is equal to the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And so that means the null space of a is equal to the 0 vector. And so that means that the kernel of t is equal to the 0 vector. Okay? Nothing in the null space, so the kernel of t is going to be the 0 vector. The range of t now, okay? I mean, there's a couple of different ways you could actually work with this. You could just say, well, okay, the range of t is going to end up being the call space of a. All right? Because the vectors in a are in R3. And if you notice, there's going to be 3 of them. So the range of t is just R3. That's probably the easiest way to look at this. The range of t equals R3. Okay, because the call space of a equals R3. And there it is. This is the second part. Is t 1 to 1? Well, kernel of t equals the 0 vector, so t is 1 to 1. Is t onto? The answer is yes, because the range of t is equal to R3, and R3 is the codomain, so t is onto. Is t an isomorphism? Yes. T is an isomorphism because t is 1 to 1 and onto. So, since t is an isomorphism, we can in fact find t inverse. And so we're going to do that. I'm actually going to go in and find a inverse first. So I go in, find a inverse, and a inverse ends up equaling 0, 1/2, 0, negative 1/2, 1/4, negative 1/2, negative 3/4, 1/8, negative 1/4. And so there's A inverse, and just like we did in the last one where we went out and found the transformation, I'm going to actually write this out as, I'm going to multiply A inverse by A, B, and C. So that's, actually, if we remember, I think I'm going to use C, B, and A, because C was the 1, B was the X, and A was the X squared. I guess it doesn't actually really matter, but we'll use CBA because that's the order we did at the beginning. CBA. 0, 1/2, 0, negative 1/2, 1/4, negative 1/2, negative 3/4, 1/8, negative 1/4. And what we get then, okay, is we're going to get 1/2 b at the top, and we'll get negative 1/2 c plus 1/4 b minus 1/2 a. Get that out, make it a little larger. Negative 1/2 c plus 1/4 b minus 1/2 a. And then we'll get negative 3/4 c plus 1/8 b plus negative 1/4 a. And that's the transformation. And all we've got to do now is we've got to turn that into a polynomial. And the reason why that's the case is that our a, or our transformation t, remember t went from P2R to R3. So T inverse has got to go from R3 to P2R. Okay? And so consequently, we're going to change this into a polynomial, right? Constant at the top. Then we have the x term, right? 1x and the x squared. So that means that t of, and we're going to have this be CBA. If you want to change it around and make it ABC, it's fine. Is going to then equal, and this is going to be 1/2 b plus negative 1/2 c plus 1/4 b minus 1/2 a x plus negative 3/4 c plus 1/8 b plus negative 1/4 a x squared. And there is the matrix of the transformation. Okay? Or rather, that's the linear transformation for T inverse. So T inverse of CBA is then going to equal 1/2 b plus negative 1/2 c plus 1/4 b minus 1/2 a x plus negative 3/4 c plus 1/8 b plus negative 1/4 a x squared. Okay? Oh, we actually just did it. Wrote this would make this I. Okay, we wrote it as a linear transformation. And now, a little extra credit. What is T of 1, negative 1, T inverse of 1, negative 1, 2? We can either use the transformation, which is fine, or we can go in and we can plug it into the matrix. I'm going to plug it into the matrix, use my calculator. Okay, so what I do here, right, I'm essentially using A inverse, and I'll multiply it then by 1, negative 1, 2. Right, and I'm using my calculator in order to do that. And that ends up giving me, that ends up equaling negative 1/2, negative 7/4, negative 11/8. And that is what T inverse is under 1, negative 1, 2. Oh, wait. You know what? That's what it is as a vector. And so this equals negative 1/2 minus 7/4 x minus 11/8 x squared. And there we go. That is what it is as a polynomial. All right, so let's suppose that we have two transformations, T R4 to R6 and S R6 to R4. Which of the transformations S or T could be 1-to-1, and then explain your reasoning. So, and we could use some pictures if we'd like. What I'm going to do is I'm basically just going to appeal to the size of the spaces. So, by the way, the phrase could be means it doesn't necessarily have to be, because this is not true for all transformations, but it is true in terms of like the relative sizes of the spaces. So what we know is that if for T to be 1-to-1, the dimension of V has to be less than or equal to the dimension of the W. All right. Basically, what we're talking about here is you want to think to be 1-to-1, we've essentially got to have every element in T goes to one and only one element in W. Okay. So if there are 4 dimensions in V, right, it's possible that we end up getting into only 4 dimensions in W, in this case, because W is actually bigger. But if we go the other way around, and this is actually the challenge here, is if we go the other way around, we're into R6, so we have more dimensions in our V instead of our domain, and we're trying to fit them into, right? Okay, so you can imagine I've got 1, 2, 3, 4, 5, 6 dimensions, and I've got 1, 2, 3, 4 in R4, and this is just metaphoric, but it's kind of the idea. So if you look here, like if we map 1 to 1 for the first 3 or first 4, then the other 2 are going to have to map somewhere, because otherwise they're not, the transformation is not well defined, but that automatically makes it not 1 to 1. Okay, so we end up having this be not 1 to 1, and so consequently, since the dimension of V is less than or equal to the dimension of W for T, T could be 1 to 1. But but S could not. S is there's no possible way for S to be 1 to 1 because of basically this thing right here. Its domain is bigger than its codomain. That's essentially the idea. Okay? Let's now look at number B. So we're going to suppose that T goes from R4 to R6 and S goes to R6 to R4. And the question that we have now is which of the transformations S or T could be on to. Then we'll explain our reasonings, and we could use some pictures if we'd like. And I think what I'm going to do here, I'm going to first get the kind of the conceptual reason as to why why we have the answer that we have, and then I'm actually going to talk a little bit, do kind of a proof one where I'm going to use the general rank nullity. So I've got T goes from R4 to R6, and S goes from R6 to R4. And so what I need in order for our transformation to be onto is I need actually that the domain, all right, has to be greater than, or the dimension of the domain has to be greater than or equal to the dimension of the range, of the codomain. So basically, for T to be 1 to 1, for T to be onto, the dimension of V has to be greater than or equal to the dimension of W. So you notice that, basically have that relationship there. It's the kind of not quite the opposite, but somewhat the opposite, right? We have the greater than rather than the less than. And so if you think about it, here's the reason why. So we've got a 6-dimensional space, R6, and 1, 2, 3, 4, 5, 6. Let's imagine those are all the dimensions. Essentially, what you can think of is that that T of 1, 0, well, in this case, T of 1, 0, 0, 0, 0, 0, right? T of E1 has to go to something, okay? T of E2 has to go to something, T of E3 has to go to something, T of E4 has to go to something, right? Okay? And so they're essentially going to go to basis vectors in R4 in some manner or another. So we've got this, here's R4 now, and so we imagine that R4 has 4 dimensions, 1, 2, 3, 4. Okay, and so in R6 we could say, okay, well, 1, 2, 3, and 4. Great, those dimensions are there. Then what we have, like we had before, we have 1, 2. 2 of the dimensions in R6 are going to go to, possibly, potentially, 2 dimensions are the same dimensions in R4 that they did in the other case, or a linear combination thereof. It doesn't really matter. It just, the idea here is that I've got 6 dimensions here in R6, 4 dimensions in R4, okay? So it's entirely possible that I map those 6 dimensions onto 4. But if I switch it around, and let's say, for example, I have R4 now going into R6, now what I've got is I've got 1, 2, 3, 4, right? We kind of imagine those basis vectors, E1, E2, E3, and E4 under the dimension, the transformation, and we have 1, 2, 3, 4, 5, and 6. So now under that transformation, E1 is going to go somewhere, E2 is going to go somewhere, E3 goes somewhere, and E4 goes somewhere, but we can't get those other 2 dimensions, whatever they are. All right, so those other 2 dimensions are not going to be mapped to. That's our problem. All right, so this transformation cannot be on 2. No way. So from that perspective, right, we can say that S, R6 to R4, is the transformation that could be on 2. So S could be on 2. Now, since this is a review, let's actually talk about another way to do this, a way that we might do this a little bit more mathematically rigorously. So we've got general rank nullity. So general rank nullity basically says that, so this is general rank nullity. And that says that the dimension of the kernel of T plus the dimension of the range of T equals the dimension of V, our input space. Okay? So what I'm going to get here, I've got a couple of things here that are going to be interesting. Let's imagine that we've got T, and it's going to go from R4 into R6. Okay? Now, the dimension of V is 4. Okay? And so consequently, the issue that we have is that if the dimension of V is equal to 4, the dimension of the range of T must be less than or equal to 4, right? Because that would be 4, and then that would make the dimension of the kernel of T, right, equal to 0. So this would end up being 0 plus 4, and that equals 4. Okay? And if the range of T, if the dimension of the range of T equals 4, then the range of T cannot equal R6, because R6 is 6-dimensional, right? Those two things can't happen, right? R6 is 6-dimensional, doesn't work. If we look the other way around, though, let's suppose that I have now S, and S goes from R6 into R4. If I do that, now, thinking about dimension rank nullity, I've got the dimension of the kernel of T plus the dimension of the range of T equal to the dimension of V. Now the dimension of V is equal to 6, right? Because V is R6. And so the dimension of the range of T could be, this is R6 into R4. So the dimension of the range of T could be 4. In fact, it has to be less than or equal to 4. So we see that we can actually do this addition. We got the dimension of the range of T is going to equal 4. All right? And then at most, right? Because it's in R4. And then the dimension of the kernel of T, right, has to be less than or equal to 2. Okay, so the dimension of the kernel of T has to be, not less than, but it has to be greater than or equal to 2, right? At least 2. And that's because the range is over here in, the codomain. And so, since the range is in the codomain, it can only be at most the entirety of the codomain. It can't be any more than that, right? It fills the space or nothing, okay? So what that means for us is that, okay, at most it's 4, and that means that the kernel of T has to be greater than or equal to 2. And this is also one of the reasons why, okay, why we end up having that S cannot be 1-to-1. And that's because the dimension of the kernel of T cannot equal 0, right? And that means, by the way, that the kernel of T cannot equal 0. Because there's only one subspace that actually has 0 dimension, and that's the kernel. That's the 0 vector. Okay, so kernel of T cannot equal 0. Right, so there that is. But you can see, actually, that it is possible. It is possible for the function to be 1-to-1. On 2. Function to be on 2. And the reason why it's possible for the function to be on 2 is because, right, we could potentially have the range of T the dimension of the range of t could equal 4, possibly. So range of t could equal R4. Something really important to get here. Don't trip here, okay? You want to hear this. Could be and is are two different things, okay? This doesn't say that that S is on 2. It's saying that it could be on 2. Could be meaning not necessarily is, but might be, okay? So if we actually know the transformation, we can determine whether or not it's onto or not. If we don't, we can't determine onto, right? Just like we can't determine one-to-one if we don't know the transformation, all right? Okay? Unless we have specific pieces of information that actually like tell us specifically how many, what the dimension of the range of t is, for example, and what v is, or kind of gives us those thoughts. So you want to notice the whole idea here, could be, does not necessarily mean is, all right? Okay, but in this case, we have two things that we want to confirm. That one is that if the transformation t, if its domain is less than its range, or excuse me, if its domain is less than its codomain, then it could be 1-to-1. If, on the other hand, the domain of the transformation is greater than the domain of the codomain, then it could be on 2, but there's no possible way it could be 1-to-1. Okay? So that's a bit of an explanation there. All right, so we got which of the following ST or TS could be an isomorphism, and then explain how you know. And what I'm going to do is I'm actually going to pull this from the review. I just don't want you to worry about it for the exam. It requires us to work through some examples, right, that I normally do in my in-person class, but since we're in an online class, we won't be talking about this one. I'll see if I can actually put together a video for it later, but for right now, pay attention, pulling this from the actual review. So let's ask ourselves, are P1R and R2 isomorphic? And this is a good question, definitely allowable. What we mean by isomorphic is we mean that isomorphic is there exists a t from P1R to R2 that is an isomorphism. So that's what it means to be isomorphic. All right. We have one first test is we need to make sure. All right. So basically, if I can construct an isomorphism from P1R to R2, if I could find one that does that, okay, then what I know is that the two spaces are in fact isomorphic. All right. And so what we want to do first is we first need to make a check. Now, this doesn't necessarily mean that the two are isomorphic, but it's an important check. We need that the dimension of P1R equals the dimension of R2. And the reason why that is that it goes into like what we talked about a little bit above, right? You can't, if their dimensions are not the same, then either the transformations will never be onto or the transformations will never be 1-to-1, okay? And so consequently, in order to have an isomorphism, we need that the dimensions between the input space and the output space have to be the same, okay? So that's cool. Now, here's the thing. Because they are, we actually can create a pretty simple transformation that is in fact going to show that the two are in fact isomorphic. So we're going to consider, let's do, we'll do P1R and R2. And we're going to take that T1, which is the first standard basis vector for P1R. We're going to set that equal to just the standard basis vector in R2. So it's going to be 1, 0. Okay? And then we'll have Tx, which is the other standard basis vector in P1R. We're going to set that equal to 0, 1. This is a standard process that we can use in order to actually find an isomorphism. In fact, what that means is that we get then that T of, and we'll call this A. T of TA is going to equal then A0. And then we'll call this TB, okay, equals 0B. or TBX, excuse me, TBX equals 0b. Okay, so if we write that as a whole, that's going to be T of A plus BX should equal A0 plus B0 by transformation. So that means that T of A plus BX equals A. That's 0b, excuse me. 0b equals AB. And there you are. And that's your transformation. You can actually go in, prove that it is one-to-one and onto. How do we know? I mean, one way is that the matrix of the transformation is literally A equals 1, 0, 0, 1. And that is most assuredly invertible. All right, and since it's invertible, that means that it is also an isomorphism. So yeah, right? How would I write this? Okay, I'm going to say since T of A plus BX equal to AB with A equal to 1, 0, 0, 1 is an isomorphism. And that's obvious. Okay, look. How about this? As A is invertible, that's, there we go. As A is invertible, P1R and R2 are isomorphic. Okay, so what are we saying here? We're saying two spaces are isomorphic if we can construct an isomorphism between the two of them, basically a bijection. Okay, find an invertible matrix that actually takes me from one space to the other space. Perfect. That's also that's basically what we're doing. So what did we do? We took our standard basis vectors in P1R and we turned them into the standard basis vectors in R2. We could do that because the dimensions of the two of them were actually the same. Okay, the dimensions of the two spaces are the same. Okay, so consequently, what you do is you just go in, you take the standard basis vectors in the input space, the domain, and you set them equal to the standard basis vectors in your codomain. Then you can construct a transformation from there. Let's say now we look at E. We're going to suppose that A is the matrix of the transformation T and A is 4 by 3. Can T be onto? This one is really asking ourselves, can we imagine what the matrix of the transformation looks like? Okay, or what the transformation looks like based upon the matrix of the transformation. So A is 4 by 3, and A equal to 4 by 3, right? What that means is that my codomain is going to be 4-dimensional, and my domain is going to be 3-dimensional. So let's say, for example, I've got dim of, that means that dim of V is going to equal 3, okay? And the dimension of W is going to equal 4. So in this case, the dimension of V is less than the dimension of W. All right? And so if you remember, in order for T to be onto, the dimension of V has to be greater than or equal to the dimension of W. This is not true, okay? So T cannot be onto. That's it, right? So one thing to notice, right? First thing to notice and get about this is that when we have our matrix of the transformation, this is the dimension of V. That's dim V right there, is going to be the number of columns. And the dimension of W is going to be the number of rows. And if you're having any problems with that, sometimes what I do is I actually go in and I draw out a picture, right? Okay, I look at this and I think to myself, okay, so actually I'm going to make it 4 by 3. So it's 4 by 3. Okay, so A, B, C, D, E, F, G, H, I, J, K, L. multiply that. That's going to be multiplied by three-dimensional vectors, x1, x2, x3. And then that'll equal a four-dimensional vector, right? Just by matrix multiplication. So y1, y2, y3, y4. So this thing here, that is my domain, right? It's three-dimensional. It may not necessarily be R3. We might be transforming something into R3, but it's still just three-dimensional. And this thing over here, okay, that is our codomain. And so our codomain is four-dimensional, right? Input space, domain, output space, codomain, and here's our matrix of transformation. So, you know, if you ever kind of like forget that kind of thing, you could actually draw out an example of the matrix of the transformation and see what you get for your domain and your codomain. After you do that, we just need to remember, or you need to think through the fact that in order for T to be onto, we need the dimension of V has to be greater than or equal to the dimension of W. So now we want to ask, suppose that A has the eigenvalue of 6 and a corresponding eigenvector of 1, negative 1, 2. What is A of negative 2, 2, negative 4? One of the things to notice here is that 1, negative 1, 2 is actually equal to negative 2 times, 2, negative 2 times 1, negative 1, 2 is actually equal to negative 2, 2, 4. All right, so what we know now is we know that, in fact, negative 2, 2, negative 4 is also an eigenvector for A. All right, by definition, eigenvectors are all of the vectors that are on a particular line of vectors. So that means that negative 2, 2, negative 4 is also an eigenvector. So what that means is that what's going to happen is I'm going to multiply A times negative 2, 2, negative 4, and that's essentially equal to A times 2, or times negative 2, excuse me, times 1, negative 1, 2. And that equals negative 2 times A times 1, negative 1, 2. By definition, this is an eigenvector. And since it's an eigenvector, what that means is that we're going to basically just stretch it by 6. So this is now going to equal negative 2 times 6 times 1, negative 1, 2. And that's negative 12 times the whole vector. That's equal to negative 12, 12, negative 24. And that is the value for our eigenvector. Or excuse me, is the value of A times negative 2, 2, negative 4. Okay? Essentially, since negative 2, 2, negative 4 is an eigenvector with a corresponding eigenvalue of 6, we're basically just going to get 6 times negative 2, 2, negative 4. And that's negative 12, 12, negative 24. And there we are. So we're going to let T, V to W be a linear transformation, and A, the matrix of the linear transformation, T, is 4 by 6, and the transformation is onto. What is the dimension of the kernel of T? So we're going to use that general rank nullity again. And so consequently, what we'll get, we're going to say, okay, well, T is 4 by 6. And so if you remember, we've got that the dimension of the dimension of V is going to equal 6, and the dimension of W is going to equal 4. Okay, so dimension of V equals 6, right? Because this is 4 by 6. Okay? Now, the other thing that I have here is that the dimension of W is 4. Okay? So the max that the range of T, or the max that the dim of the range of T can equal is, in fact, 4. Okay? So the max of the dim of the range of T is equal to 4. And so consequently, what we have here is we have, all right, that's going to like kind of limit what's happening when we use general rank nullity. All right. So we do, however, know that the dimension that the transformation is onto. Okay. So since the transformation is onto, what that means is that the dimension of the range of T is going to equal the dimension of W, because the range of T equals W because t is on 2. So that's just what's going to happen. T is on 2, so we're going to have that the range of t equals w, and so the dimension of the range of t is going to equal the dimension of w, and that's going to equal 4. So now general rank nullity which says the dimension of the kernel of t plus the dimension of the range of t equals the dimension of v. I know the dimension of v is equal to 6. I know the dimension of the range of t is equal to 4. And so that means that the dimension of the kernel of t is equal to 2. 2 plus 4 equals 6. So the dimension of the kernel of t is equal to 2. And there we are. Clearly, t is not going to be 1 to 1. All right? So, again, a couple of pieces of information here that are going to be kind of handy. T is 4 by 6. Okay? So that means that the dimension of our input space is 6. The dimension of w is going to end up being equal to 4. The maximum dimension of the range of t is going to equal 4 because the dimension of the w equals 4. But we know that the transformation is on 2. So since the transformation is on 2, that means that the range of t does equal w. So the dimension of the range of t equals the dimension of the range of w. Then all we got to do is plug this into our general rank nullity. The dimension of the kernel of t plus the dimension of the range of t is equal to the dimension of v. 2 plus 4 equals 6. So the dimension of our kernel of t is going to equal 2.